theorem. There are infinitely many primes of the form 4n plus 3. Proof. Here, proof is by contradiction. So if you take from contradiction, is very easy to prove. So proof is by contradiction. So here proof is by contradiction means here they given infinite, right? So infinite means you have to take opposite that one. So you have to take finite many primes here. So suppose there are finitely many primes. Finitely many primes of the form 4n plus 3. Say p1 comma p2 comma p3 comma so on up to pk. So now I'll define, let m equals 4 times of p1 p2 p3 so on pk. Here don't write like this p1 comma p2 comma p3. This is product, so p1 p2 p3 so on up to pk minus 1. So m is of the form m equals 4n plus 3 with n equals p1 p2 p3 so on pk minus 1. So this m, it is in 4n plus 3 form. So how will you get that one means here, so what they have here 4n plus 3. So what is n I taken here? 4 times of p1 p2 p3 so on pk minus 1 plus 3. So what you get? 4 times of p1 p2 p3 so on pk minus 4 plus 3. So what you get? 4 times of p1 p2 p3 so on pk minus 1. So we get same thing. So this is in the form 4n plus 3. So now here since here 4n plus 3 is an odd, right? So since m is odd integer or odd primes, because you're proving for prime number here, primes. So we have p1 p2 p3 so on pk are all odd primes Very stop. So pi is of the form, pi means this one, pi means this thing, is of the form 4n plus 1 or 4n plus 3. Here odd means you will get two types. One is 4n plus 1 is also odd and 4n plus 3 is also odd. So for some n, for some n. So if I take 4n plus 1, what happened? Let's check it. So here if 4n plus if each such pi is of the form 4n plus 1, then what you get m. So here what you get here, let's check it. So here suppose if I take here 1 5 13, so all are odd primes only. So if I take product of these two, 1 5s are 5, so what you get here, this can be written as 4 into 1 plus 1, that means 4n plus form you written here. So what you get, 5 plus 1, 4 plus 1 you will get an 5. So if you take whole this part, so what you get here, 5 13s you will get 65 into 1 you will get 65. So 4 into 16 plus 1, 4 16s are here 64, 60 plus 4 1 you will get 65. This is also in 4n plus 1 form. But if you go on for like that only, if you go on continue like this, somewhere you will get 4n plus 3, not you will get an 4n plus 1, sometimes you will get an 4n plus 3 also. So what happened here, then m is also you will get 4n plus 1 only, but which is false, which is false or not true. So here hence m is divisible at least one prime, one pi prime pi is of the form, one pi of the form, what is that one, that is 4n plus 3. Here somewhere you will get pk, right? Somewhere you will get divides 4n plus 3 also here. So what you get, that is of the form 4n plus 3. So here what happened, pi divides m and pi divides 4 times of p1 p2 p3 product, divides the product. So that means pi divides 4 times of p1 p2 p3 so on pk minus m, because here a divides b and a divides c means then a divides b plus or minus c, means product here addition also it divides or subtraction is also divides, so that one you written here. Okay, so this is what you get here. What is m equals 4 times of p1 p2 p3 up to pk minus 1, right? So interchange these two. So what you get, if you go to plus 1, it will go to here, minus m will get. So this can be written as 1. So that means pi divides 1 here, because here 1 equals 4 times of p1 p2 pk minus m. So here pi divides 1 means here what I get here, in prime, always in prime, always n is greater than 1. So here we get 1. So which is impossible, means therefore here finite is not possible. We taken starting here, finite here, there are finitely many primes. So which is not possible means there are infinitely many primes. So therefore there are infinitely many primes is of the form 4n plus 3. Theorem. If p of n is the nth prime, then p of n is less than equal to 2 to the power of k minus 1 for all n is greater than equal to n. This is not here, this is n. So n minus 1 for all n is greater than equal to 1. Now proof. So we prove by mathematical induction this theorem. So we prove this by mathematical induction. So here now we discuss about mathematical induction. So what you get here in mathematical induction, p of n is true for n equals 1, and then p of n is true for n equals k. So p of k plus 1 is also true. So here p of k implies you will get p of k plus 1. So here if you first you have to prove for n equals 1 and n equals k, afterwards you have to take for n p of k plus 1. So k plus 1 afterwards you have to take. So first we assume here what we get here, we know that p of n, what they given, p of n is less than equal to 2 to the power of 2n minus 1, right? So put n equals 1. So what is p of 1 is less than equal to 2 to the power of 1 minus 1. So 2 to the power of 0. So 2 to the power of 0 means it is 1. So 2 to the power of 1 will get, so we'll get 2. So that means p of 1 equals 2. So what are the prime numbers? The prime numbers are 2, 3, 5, 7, 11. But what is first prime number? First prime number is 2. So here prime number p means prime. First prime number is what is 2. So therefore p of 1 is true. Next we have to assume that here n equals k, you have to substitute. So if we put n equals k, what happened here? So wherever n is there, for this one, wherever n is there, you have to substitute k. So pk is less than equal to 2 to the power of k minus 1. So this implies that p of k is true for all k is greater than equal to 1. K is greater than equal to 1. Now I will consider here. Next we have to prove for p of k plus 1. So I will consider here pk plus 1. pk plus 1 equals, I will take prime number here, product here, sorry, p1, p2, p3, so on, pk plus I will add another prime here plus 1. So this implies that is less than equal to, here p means it is 2 and p2 means if you put n equals 2 for this one, you get 2 to the power of 2 square, and if you put n equals 3, you will get 2 to the power of square, so on. If you continue like that, what do you get? K here 2 to the power of k minus 1 plus 1 you get. So by here, you know GP here, right? Geometric progression. So what do you get here? Geometric progression. So I'll consider 1 here, 1 plus 2 square plus so 1 plus 2 to the power of k minus 1. So what is the geometric progression formula? R to the power of n minus 1 divided by r minus 1. So here what happened here? A means what you get? It is 2 divided by 1. Here a, this is 1, a means. So what you get? First element is 1. So what you get here? R means common difference. So you have to divide this one. 2 divide 1, so you will get 2. So 2 square divided by 2, you will get 2, again 2. So that means common difference is 2. So R value. So 2 to the power of n means you have taken here k, right? So this is becomes k. 2 to the power of k minus 1 divided by 2 minus 1. So what happened here? 2 to the power of k minus 1 will get. So substitute that one. So less than equal to 2 into this I written here. So what is the power will get? Power is 2 to the power of k minus 1. 2 to the power of k minus 1. So here it is plus 1 is there. But 1 is less than 2 to the power of 2k minus 1. 2k is the minus 1 here for all k is greater than. Here if you put k equals 1, greater than equal to 0, so this is also less than. So if you put greater than equal to 0, this becomes 1 to the power of this becomes 0. So 2 to the power of 0 is 1, 1 minus 1 0, 2 to the power of 0 is 1. So 1 equals 1 will get. So wherever 1 is there, I am substituting this one here. So it is less than equal to 2 to the power of 2k minus 1 plus 2 to the power of 2k here minus 1. So this implies that 2 times of 2 to the power of k here minus 1. So this implies that it is power is 1. So if you add, what you get? 2 to the power of 2k minus 1 plus 1. So this implies 2 to the power of 2k. So that means what you get here? If you replace k to k plus 1, so what you get here? Here also you get k plus 1 will get. So 2 to the power of 2k only. That means here what you get here? What is p of k? P of k is less than equal to 2 to the power of 2k minus 1 is there. So if you replace k by k plus 1, so what you get? 2 to the power of 2 to the power of k plus 1 minus 1. These two get cancelled. So 2 to the power of 2 to the power of k will get. So both are same. So therefore the the p of k plus 1 is true. So this implies, therefore, hence by induction, mathematical induction, Pn is true for all n is greater than equal to 1. So this is the proof. Now I go for one definition, that is Fermat number and Fermat primes. So here number of the form Fn equals 2 to the power of n plus 1 are called Fermat number and those which are primes are called Fermat primes. Yeah, in this, if you put n equals 1, 2, 3, so on, so whatever you get prime numbers, so that prime numbers are called Fermat primes. Now Mersenne, Mersenne, Mersenne number and Mersenne primes. Mersenne prime. So number of the form here Mn equals 2 to the power of n minus 1, where n is a prime are known as Mersenne numbers. And those which are prime. That means if you put prime numbers means 1, 2, sorry, if you put prime numbers for n means 2, 3, 5, 7, 11 like that. In those, if you get prime numbers, those prime numbers are called Mersenne primes. Mersenne primes.